So this is very, very small compared to 1. So this will remove. So basically what you get is, and also the fluid approximation is such that there are no charge separation fields. So the time scales in which you are working is 1 over plasma omega Pe. Tau is proportional to 1 over omega Pe, which is typically nanoseconds. And then the scales, space scales, are typically much larger than the Debye length. So in this, under these conditions, the fluid equations are valid. So in that sense, the E is also 0. So basically you are saying that the time scales and the space scales that we are interested, there are no charge separation fields. Charge separation means electric field. So therefore, this equation basically reduces to M E N E B is basically J. So J cross B is equal to grad P. So now let us dot it with B. So this goes to 0. Now what you get is same thing is true if I dot with J. So J dot grad P is also 0. Now when I say this is 0, either this is 0 or gradient of pressure is 0. But B we know it is not 0. So gradient of pressure has to be 0, which means pressure is constant. So therefore what is happening now is you have a plasma. You have a plasma on which you have this B and J. They are crossed with each other, so they are in the two different coordinate system. So J and B, this is the gradient of pressure. So therefore, you'll see that what you are forming is isobaric magnetic surfaces. So basically, because this quantity is 0, it is something like both the quantities are on surface. So basically, B and J are surface quantities. So basically, they are on the surface of the plasma, whereas gradient of pressure is this way, in the radial direction. So therefore, what you are forming is basically magnetic surfaces on which pressure is constant. Pressure is constant का मतलब क्या हुआ? N and KT, temperature, both are constants. So on these surfaces, pressure is constant, मतलब both density and temperature are constant. So therefore, this is a very important application of the fluid equation, which says that you the whole plasma now has been, there are magnetic surfaces formed on which both density and temperature is constant, which means pressure is constant. So therefore, this is basically the basis on which magnetic confinement schemes work. Magnetic confinement, आपने सुना होगा ना? There are different types of confinement of plasma particles. You can have either inertial confinement, gravitational confinement, and magnetic confinement. So gravitational confinement, you have in the sun, you have got gravitational confinement. Particles are confined because of the gravitational field. Inertial confinement is basically the inertia of the material itself. I'll not get into that. Sometime later I can discuss to you the physics part of it. But the magnetic confinement scheme, the basis is this. Which means that you have magnetic surfaces on which both density and temperature are constant. So there are particles moving along the field lines. You have formed surfaces. So all the particles now will move on surfaces. So they will not leave the surface unless there are collisions. So only collisions can move one particle from the surface to another surface. So what will have basically what you will observe. If this is the vacuum vessel in which you have formed the plasma, so you have plasma formed this way. What you will have is neat surfaces on which pressure is constant. So all the particles will start moving along the whichever is following the field lines. They'll all follow this surfaces. So these are called nested surfaces. So this is the basis for magnetic confinement schemes. So very important concept. Basically, you are forming magnetic surfaces on which particles are confined now, and any motion of the particles away from this is only because of collisions. If there are collisions, the particle will leave one surface and go to the another surface. Again, when it gains energy, it will go back to the surface. So it will follow this surface strictly. So it's something like it is tied. The particles are tied to these surfaces. Okay, there's something like a net formed. All the particles will now go along the net, unless there are some instabilities or collisions. These particles will not leave that surface. So particles are confined by these surfaces. So very important concept of magnetic surfaces. The whole magnetic confinement scheme is based on this particular concept. Okay, so just remember this in a very important concept. Another interesting component. So what we have seen is basically magnetic surfaces. Very important. Similarly, you have magnetic pressure. So any field line, if you have, if this is the field line, so it will exert a isotropic pressure. So you will have a pressure in all homogeneously applied, which is basically given by. So this is called the magnetic pressure. So every field line will have a sort of magnetic pressure. Okay, and now you can also write an equation for the tension in the field line. So that tension is basically twice this magnetic pressure. So very important concept. So it is something like a string, if you have a string and you just vibrate at one location, there will be waves moving along the string. So something similar will happen to the magnetic field lines also, because there is a tension in the magnetic field lines. If you do small perturbation at one end, that perturbation will travel along the field line. So these are called alpha waves. So these are magnetic pressure. So two important concepts: magnetic surfaces, magnetic pressure. So now, as I told you, so it is something like a string, a tight string. So if you perturb the one end of the string, there will be perturbations traveling along the length of the string. So that is something called the alpha waves. We'll do more of this when we'll talk about the next topic, waves in plasma. But remember, you have a magnetic field, so it has a tension which is given by twice the magnetic pressure, and magnetic pressure is basically b square by 2 mu naught. What is mu naught? Mu naught is 4 pi minus 7 Henry, if you remember. Okay, so you can as well write it as 8 pi. So basically, magnetic pressure is b square by 8 pi. Okay, so another important concept, there's a associated with every magnetic field line, there's a tension which is twice the magnetic pressure, and magnetic pressure is basically b square by 8 pi. So these are Alkin waves. So you should we'll discuss more on this when we go to the next topic of waves in plasma. So basically, they are waves along the direction of the field line. Field. So parallel to the field. Yesterday we saw there was something perpendicular to the field, which is the diamagnetic drift. So these are waves along the field lines. Okay. So related to this, basically there's another quantity which is called the beta, which is the plasma pressure by magnetic pressure. So plasma pressure is what? N ET divided by b square by 8 pi. So this quantity is very, very important. It tells you the efficiency of magnetic confinement, how strong the field should be to confine this kind of plasma, which has this density and this temperature. So efficiency of confinement of plasmas by magnetic field. So that is given by this quantity which is called beta. It's basically nothing but plasma pressure divided by the magnetic pressure. So this is the quantity. So every tokamak or every plasma device will have a particular beta. You cannot exceed this a particular quantity, because the moment you try to increase, plasma pressure will become stronger than the magnetic field. So therefore it will break the field lines. So there are instabilities which are generated. So there is always a given beta. You cannot exceed this beta. So this ratio is important. So for any device, for a given magnetic field, the pressure is known. You cannot continuously keep increasing the pressure. The moment you try to increase the pressure, the plasma particles will become much, much more energetic. So they will try to distort the magnetic field lines. So that is how you lose the confinement properties. Okay. So these are some important applications of the fluid picture. I think I'll share my notes with you people so that it becomes clear for you. I'll scan my notes and then send it to you people. Okay, so going over to the next topic. I thought something before we close down on the fluid picture of the plasma. I would like to slightly tell you something about the kinetic picture of the plasma. So, little bit about the concepts of kinetic theory of plasmas. So, what we saw was, if I have to write down the collision list, Boltzmann's equation. So basically, I can write it down in terms of the distribution function equal to 0 because we have not put collisions still. There are no collisions, so it's a collisionless Boltzmann's equation. But let us see now. In a plasma, basically what you can do is, for this term, what you can write it as F by N, dou F by dou U. So F basically is E plus V cross B. This is the force. And you can also add gravitational force if it is there. But gravitational forces are quite weak compared to the forces that we are talking about. But you can always include that quantity. So this F is basically these things. So when you put all these things, and now these fields are basically electric magnetic fields applied externally, but also you have to take into account the internal electric fields and magnetic fields, which are generated, self-generated by the plasma. So you have to write a self-consistent equation. Self-consistent because the external fields are now will get modified because of the motion of the charged particles inside the plasma. So all those things will now go into E and B. So these are not just the external magnetic field, it's the magnetic field, total magnetic field, which is the external field plus modifications done by the plasma particles. So when you put these equations, this Boltzmann's equation becomes Lasso equation. Lasso, VLASOV. You're able to see this portion? You're able to see this portion.
Yes,
So
sir.
this equation now gets converted into, from Boltzmann's equation. Boltzmann's equation is for neutral particles. So the plasma के लिए what happens? E and B now gets modified by the plasma particles. So when you write the equation, instead of U prime, U is basically acceleration. So instead of acceleration, I can write F is ma or A is F by m. So that is exactly what I've written. F by n. And for F, you put in all these values, E and B. So that becomes the Lasso equation. Now, there's a very important concept like what is the difference between the Lasso equation and the Boltzmann's equation? Boltzmann's equation I can write for the plasma also. What is it? How is it different? The way it is different is somehow very approximately collisions have been put into the Lasso equation. So in that sense, they are different from collisionless Boltzmann's equation. Collisionless Boltzmann equation matlab there is no term which has f of et which is collisions. If I add that, I had written the equation as 0. Instead of 0, if I add this portion and write a particular expression for this, so I'll be taking into account the collisions into the Boltzmann's equation. So till the time I have not taken the collisions in the Boltzmann's equation, this and Vlasov equation, they are almost similar, but slight difference because a very approximate, like long distance effects of particles. Like if an electron is here and an ion is here, so the effect of this on this, the trajectory of equation of motion for the electrons because of the presence of this is somehow taken into account in Vlasov equation. Okay. Whereas collisionless Boltzmann equation, we have put it 0. There is no term describing collisions. I'll show you how I can still put collisions into this. We'll discuss when we go a little further. So now this Vlasov equation, if it is allowed for some time, so the thermodynamic equilibrium will not give rise to Maxwell's equation, Maxwell's distribution, because Maxwell's distribution is because of the collisions. Only when there are collisions, you get Maxwell's distribution. So from Boltzmann's equation to the Maxwell's equation, Maxwell's distribution, that comes because of collisions. There are collisions between particles, so that is how energy momentum transfer takes place. So if you allow this collisions to go on for a very long time, you will have an equilibrium, thermodynamic equilibrium. So that will give rise to Maxwell's equation, Maxwell's distribution. So I told you Maxwell's distribution is f of v versus v. It will have a distribution of this kind. So particles are distributed in velocity like this, and that happens only if there are collisions. And because Vlasov equation may, I have not put collisions precisely. I have only taken the effect of charged particles from a distance. I have not taken into account large angle scattering, which means collisions are not fully put into the equations. So therefore, Vlasov equation will not lead to Maxwell's distribution. This distribution. This distribution will come only from Boltzmann's equation, which has collision term. Instead of 0, if I put collision term, there are collisions going on between all the particles, electrons, ions, neutrals. So that is how energy. Yeah, is there a question? Darshan?
No, sir. No, sir.
Okay. So only when there are collisions, the final thermodynamic equilibrium, in that state you will get all the distribution of the particles in this velocity will show up this kind of a distribution, which is called the Maxwell distribution. So that you should remember that Vlasov equation, though collisions have been taken into account, not really strictly, okay, only some variation of the equation of motion of an electron because of the presence of ions far off has been put into it. Otherwise, you don't have a. Basically, I can write down the equation for that. So you will have these integrals which are basically taking part. So these are called the two particle correlations. So this is basically giving rise to collisions. Because of this term, there is a change in the distribution function. Because the collisions are allowed now. So this is the quantity which takes into account, which is neglected in a Glassware equation. Glassware equation may we make this equal to 0. This G of which is the two particle correlation function. We make it equal to 0. If you actually take this into account, what you get is Fokker-Planck equation. आप लोग ने सुना होगा इसके बारे में. Fokker-Planck equation. उसमें क्या है? You will take all the particles, two particle correlation functions, three particle correlation functions. So you are truncating the whole equations to the three particle correlations. But actually, strictly speaking, it is n particle correlations. So n particle will be difficult to take into account, not practical. So what Fokker-Planck equation does is that it will truncate it to, you take the two particle correlation, but not the three particle correlation. So it still doesn't take into account large angle scattering. So see, they have discussed this part, that if there's an ion here, the electrons, even before they come very close to the ion, the trajectories are this way. They don't come. So this is a small angle scattering. Large angle scattering will come when the particle will go very close to this, and then you have, this is the angle, alpha. This is alpha. So this kind of electrons getting scattered in this direction. So these are called large angle scattering. So these kind of scatterings are not taken into account in the Planck's. It's very difficult to take into account these things. So what the Fokker-Planck equation does is, the concept basically, it says that only two particle correlations, three particle correlations are neglected, which means that you will have only small angle scatterings, no large angle scattering. That is because this is drastically going to change the direction of the particles. See, it was coming in this direction, now it goes in opposite direction. Whereas here, there's a small change. So small changes are allowed, not a large variation. So something like a random walk and all, you can explain by Fokker-Planck equation, but not this kind of trajectories where there's a drastic change in the trajectories. Okay, so that is an important thing about the Fokker-Planck equation. So just get an idea of Glassware equation and Boltzmann's equation. They are similar. If you don't take collisions, you will have collisionless Boltzmann equation, which is very close to Glassware equation, but these two are not exactly identical. There's a small difference that large angle, there's a distance when the particles are too far off, that effect is taken into account. Whereas in collisionless Boltzmann's equation, that is not taken into account. So that is the only difference between this and the Glassware equation. Whereas Fokker-Planck equation is one step ahead. It takes into account the two particle correlation, not the three particle. Okay. So something like, there's something called hierarchy. I told you about two particle, three particle, and n particle correlations. So there is something called a theory of hierarchy, and that hierarchy is basically given as, so this is the hierarchy. So this theory takes into account all those multi-particle correlation functions. So these are given by different names of the scientists. So this is Bobligobov, he's a Russian scientist. Then Born, Green, Kirkwood, and last is Bjorn. So these are all the scientists who contributed to this BBGKY hierarchy. This is called hierarchy. So the first hierarchy is taken into account in the Glassware equation. The second is taken in the Fokker-Planck equation. You cannot take a n particle correlation function. That becomes, you can do it on a computer, and even that you require a very fast computer with parallel processing and things like that. It cannot be done by a normal compiler. Okay, so in the time of you're talking about the random walk and things like that, so Fokker-Planck equation gives you almost similar results. You know? I think that much for the fluid picture of the plasma. Next, probably I'll have to take into talk about the waves in the plasma, for which I'll need little time. Okay, so next class you may not have. I thought of having a class on Saturday, but I think I'll drop that because I need little time for preparation for that class. So that is about the fluid equations, the fluid picture of the plasma. So any questions or clarifications required? Anyone, please give your comments. You may have to go through the notes that I have sent you. Some part of it is there, but I'll also scan my notes that I have presently with me. So I'll scan that and also send you. So most of the things that I've taught you is there in those notes. But you can always find from books like Bittencourt has most of it. Then I have taken from Goldstein and Rutherford. There is another book. There is one more book by Dandy. So these are some 4 or 5 books which I have followed. Chen will give you a little bit about it, but you cannot get into too much of physics from that. But it will be a good starting point. Okay. So coming to my other topic, generally we discuss something which is off the syllabus. So today I'm going to talk about something called, there's a very nice book by Usefulness of Useless Knowledge. The usefulness of useless knowledge. So basically, this is a book written by Abraham Ketchner. basically the founder director of Institute for Advanced Studies in Princeton University. The topic looks little funny because he is talking about usefulness of useless knowledge. What he calls as useless knowledge is basically basic sciences, fundamental sciences, because he had a lot of problems in getting funding from the US government for doing fundamental research. So when he actually presented his proposal to start this activity in this institute, the Congress people, they made a statement that the fundamental research is basically a useless knowledge. So that is the reason why he wrote this book of usefulness of useless knowledge. What he means by useless knowledge is basically the fundamental research. So in this book, he describes a lot of fundamental research which changed the whole society, and how it changes people never even imagined, So something like, for example, the GPS, global positioning system, is basically from the general theory of relativity. So when Einstein worked on general theory of relativity, I don't think he was ever bothered about GPS. But now we cannot do without GPS. Probably most of you must have already felt, if you go from one place to another place, another city, and you want to move around, you need a GPS system. So that basically came from the general theory of relativity. So when Einstein worked on this kind of a subject, he never bothered about GPS. But therefore, this person, Abraham Flexner, what he says is that these researches, fundamental research, is very, very important. And basically, research is driven by pure curiosity, freedom, and imagination. So they are not worried about applications part. So in this book, he talks about plenty of such inventions or discoveries done in physics, chemistry, and other sciences, where the scientists never bothered about applications before. For example, one I can give you is the discovery of X-rays. See, Röntgen never worried about whether it will be useful for medicine or things like that. But now you go to any hospital or any doctor, without X-rays, I don't think they can do any further investigation or therapy or whatever. So medicine is basically now fully equipped with X-ray units. So it tells you everything about what is happening inside. But Röntgen, when he discovered X-rays, it was purely for curiosity's sake. He never did research for seeing that his work should be applied to medicine or applied to other fields. So therefore, this author, what he talks about is usefulness of useless knowledge. Useless knowledge is basically fundamental research. So he has taken up plenty of such examples where the scientists would have never bothered about. For example, quantum theory. It has given rise to now quantum computing. See, the people who work like Planck and Heisenberg, all these people never bothered about whether this can be used for applications of this kind, But now you see that quantum computing has become very, very, it's out of the present situation, They're doing lots of research on this area. But the fundamental research was basically on quantum theory. Okay? So the book deals with that. In addition, you have a TED talk by Robert de Graaf, Robert de Graaf. So, as I told you, Abraham Fleischner was the founder director, and the present director is Robert de Graaf. So, there's a nice TED talk given by him on the same topic. So, again, he also talks about various fundamental research, even including topics like fractal geometry. So, you'll be amazed how people worked on areas fully driven by curiosity. They were not worried about applications. Applications, other people have to worry about. So that is the theme of this book. I think I'll share this book with you people. Very interesting physics experiments are discussed in this. Cosmic rays. They have covered every damn fields of physics. Cosmic rays, X-rays, radiation physics, nuclear physics. So you'll be amazed to read this book. And fundamental research like magnetic resonance. People who worked on it, they were purely driven by curiosity. They just wanted to know how the magnetic moment of a proton gets flipped if you have an external magnetic field. It was just a curiosity to know how the protons will behave to the external magnetic field. But see, that has become a useful application in medicine now. Magnetic resonance imaging is one of the important imaging for any activity in medicine now. So I hope you will get excited by this book. I'll share this book with you people. Also try to see this TED talk given by Robert de Graaf, who's the, I talked about this Institute for Advanced Studies, Princeton University. He was the founder director, and the present director is this person. So I'll share this book with you people. Read it, and we can have a lot of discussions on this. When you read this book, I think you should discuss among yourselves also how discoveries in a particular field affects a lot of other fields. Particle acceleration. Now people are talking about in medicine and many other fields, material science. So I think it needs a lot of discussion, and I think you people are the right people to discuss these kinds of topics. And anyone gets more feedback, we can discuss this in more details. So that's it. Any queries or questions from you people? Did you read my other books that I have shared with you people? The one which I sent recently. What was that? Gear Theory. You should read that book. It's an excellent thinking, how to think of Earth as a living being. It increases your sensibility for Earth, and then probably things will improve. I think whenever you get time, please read and get. I need a feedback from you people so that new ideas can always come from you people. Okay. So I'm just waiting for some feedback from you people. If there are some feedback. And the next topic that we'll talk about will be the waves in plasma, for which I'll need a little bit of time for my preparation. Hello, I hope you people are listening. Okay, then I think we'll call it a day. Have a good day. There's some है ना? I don't know whether you people are there because I'm not getting any feedback from you people. I don't know whether you people are there. So can you just say hello? Any one of you?
Yes, sir.
Okay.
Yes, sir.
Oh, thank you.
Yes, sir.
So please read some of these books. Then we can discuss some topics on this. Very interesting books. I'm sure if you start reading, you'll not like to leave those books. And it's all related to us. We are all scientists. You're all would-be scientists. I'm sure you're exploring various fields to work in. You should take up fields where there are challenges. Don't go for वो घिसा पीटा काम मत करो आप लोग, उसमें दम नहीं है, घिसा पीटा काम में दम नहीं है बिल्कुल. You should think of something off the box, out of the box. So you will find such topics from in some of these books. Areas, being a physicist, you can always get into other things, soft, more soft targets like biological physics, biochemistry. See, there's no limit now. So people can expand like anything. And we are there to help you out. Any discussions you need, we can always discuss with you people. Okay. But I'm looking forward to your feedback on any of those books which you have received from me. Okay. Good luck to all of you. See you again. Okay.
Thank you, sir.
Bye.
Students, you now